Hello. Today I'm going to talk to you about the equation for calculating the force, the electrical force between two charged particles. So, for example, say that we have two charged objects. We might have one here and one over here. And you say, well, maybe this one is charged positively and this one's charged positively. Then you'd say, well, I know from the fundamental rule of charge that like charges repel. So this charge would be being pushed this way by the electric force, and this charge would be being pushed away from that guy this way by the electric force. And so the first question I would ask is, hey, how do you suppose the size of this force compares to this force? And you, of course, would say, well, they're going to be the same because they're really not two different forces. We define a force as an interaction between two objects that results in a push or a pull. So this is one interaction between these two things. They shove on each other. And so when I'm really calculating, this is going to be the same size as this. That's what I'm going to calculate, is the size of this force. So we might consider, what different factors do you think are going to affect how big the force is between these two charged objects? So one thing that you might think about is to say, well, I know that, say this is like a metal sphere or something, and I've stripped some electrons off it to make it positive. You say, well, I could, strip some more electrons off, make it even more positive. I could change the amount of charge. And I know that every unbalanced proton in this guy is going to push on every unbalanced proton in this guy. You say, well, what if I had stripped twice as many electrons off? Well, wouldn't that be just as if I had like two of these guys pushing, right? You know what I mean? And so if there's two of them, well, he's going to push just as hard as this guy pushed, right? And so it would just, basically double the force then, right? And so you say, well, that means the amount of charge I have here, if I double it, it would double the force. If I tripled it, it would triple the force. That electric force should be directly proportional to how much charge we have here. So electric force, um, then we're going to say, should be proportional to charge. Now, the symbol that we use for charge, right, we're going to say is directly proportional. The symbol we use for charge is a Q, all right? You can think of that Q as standing for the quantity of charge, the amount of charge. Now, I could double the charge here, and then each of these is going to push this guy and get pushed back by this guy. You say, but what would happen if I doubled over here? Right? I could make this guy twice as big, and then each of these would be pushing on each of these, and so then the force would double. So the point is that, he would get pushed by him, he get pushed by him. So if I double that charge, I'm going to double the total charge here too. So the point is, it's proportional to the charge on this side, and it's proportional to the charge on this side. So now that I've cluttered my diagram, we could talk about how much charge is on this object. And I might call the charge on this side Q1 and the charge on this object Q2. So my electric force should be directly proportional to Q1, and it should be proportional to the charge on the second object, Q2. So you might ask, okay, well, what else affects how hard these guys push on each other? And so from playing around with charged objects in class, writing like the charged tapes, doing the sticky tape lab, and playing with the pith ball and the charged rods, we noticed that how far apart the charges are affects how hard they push on each other. We said the farther apart they get, the weaker the force gets. The closer they get, the stronger the force gets. Mhm. So we're saying, okay, well, that should have something to do then with this distance between them. Okay, how far apart they are. Now, the symbol that we use for that distance, typically, you'll see different things used, but we're going to use a lowercase r. Okay. The reasoning behind that is, if I'm thinking about just one charge for right now, and you say, hey, if I put another charge out here somewhere, it might push like this on this guy. And I put a charge here, it might repel this way. And put a charge here, it might repel this way. And put a charge here, it might repel this way. And the point is, those forces are all going to be pushing out like along the radii, the radius of this guy. They're going to be pushing out in the radial direction. So these forces are always going to be like kind of radiating out from the charges. So we're going to talk about the distance in the radial direction. Kind of like if I did a distance in the x horizontal direction, I call it x, or vertical y. We're going to call this r. It's kind of a traditional thing to do for this, right? So what we can say is, now I know that when r gets bigger, I need the force to get smaller. So that kind of implies that I'm going to have that distance in the denominator, right? So as r gets bigger, the force gets smaller. When you look at this, you're going to say, well, with these, I could argue that if I made the charge twice as big, there'd be like twice as many charges pushing, and so the force should be just that many times bigger. I could argue that this were directly proportional. But do I know that this is just 1 over r? Do I know that if I doubled the separation distance, that it would make this then half as strong? Do I know that? Or tripled would be 1/3? Well, I don't really have justification for that. So what I could do is I could say, well, this is 1 over r to the n power. There's some exponent there that I don't know. Now, in class, we kind of played around with it a little bit, and we noticed that if I had like a, I don't know, sticky tape or a pith ball, a charged object hanging there, and I brought some of the charged object nearby, like maybe we bring like one of those charged rods nearby. You notice that when the charged rod is way over here, right, the pith ball basically sits still, and as we bring it in, it barely kind of starts to deflect, and then when we get close, it like suddenly like swings up really far away. So it's like if I drew a graph of how big that electrical force was versus how far apart the things are. When they're really far apart, that force was like really small. And then it barely changes. And then when we got close, it was like it suddenly shot up. So that's kind of our first inkling that this isn't just it might be something more extreme than a 1 over r graph. But the real logic behind this, behind what the exponent is, comes from thinking about a diagram like this. All right, so let me make this a little bigger. Imagine, if you would, that I'm going to do a picture. I'm going to make a special kind of diagram here. We're going to say that we have a positively charged object here. And what I want to do is I want to draw a diagram to show this guy's influence, his like electrical influence in the space around him. So like, how would he affect other charges nearby? Now, we're just going to show how he would affect positive charges nearby. So what I might do is I might imagine putting another little positive charge down here. Now, if I set a little positive charge down there, this positive, they would repel, and this guy here would get pushed away. Now, if I moved him farther out, he would get pushed away, but not as hard. Move him farther out, he'd get pushed away, but really not as hard, right? And that force would get weaker. I could draw this picture here too. Or if I put a little charge here, he get pushed away like this. Put him here, he get pushed away like this. Put it here, he get pushed away like this. And I'm kind of building up this picture of what this guy's influence looks like, his electrical influence, like how he would push on positive charges. Now, the nice thing about this diagram is if I were to put a negative charge out here, it would just get pushed the opposite direction. But I can still see by the length of the arrows kind of the idea that he's getting pushed real hard if he's close by, and this guy's influence is weaker as you go farther away. this kind of diagram is called a vector field diagram. I don't want to get too in the weeds on this, but this is kind of a nice diagram kind of showing this guy's influence. Well, the problem is I can see from like the length of the arrows kind of how strong the force is, and by how long the arrow is, sorry, how strong the force is, and by the direction of the arrow, I can see which way this guy would push a positive. I know a negative would get pulled the opposite way. But it does take a long time to draw all those little arrows. So there's a shorter way of doing this, right? That ends up being really handy for us. And that is, instead of drawing all these little arrows, we're just going to draw one long arrow out instead. When I do this diagram now, these long arrows I'm drawing are called electric field lines. Okay, so these guys are called electric field lines. And this diagram is called an electric field diagram. Now, looking at this, you say, well, I'm thinking about this guy's electrical influence kind of spreading out in space. And I'm thinking about it actually happening in 3 dimensions, kind of coming out in all directions from this guy. His kind of electrical influence spreading out. And so it's going to push or pull on other charges that are in the space near it. Now, you know that this guy's influence will be really strong when you're close, and it'll be weak when you're farther away. I was trying to show that before by how long I made the little red arrows, but now instead of the red arrows, I'm just using these long green arrows. So you might think that I've lost that information. You're like, hey, from the green arrows, I can see which way he would push a positive charge. But I've lost the information about how strongly he would push and how strong his influence is. Well, it turns out that information is still coded in this diagram. It's just coded in a different way. When we draw an electric field diagram like this, the only way of thinking about it is this influence as you go farther away. You notice these field lines get farther and farther apart. And so what that's showing you is that the field's getting weaker. How tightly packed those field lines are tells you how strong this guy's electrical influence, his electric field is. You can kind of imagine if this was like a source of light, that as you go farther away, the light kind of gets spread out more. It gets more diffuse, less intense, and it's getting weaker. Same sort of kind of a similar idea, this having to spread out in 3D. So I can think about how tightly packed the field lines are. It tells me how strong the field is. That goes like this. Field strength is going to be equal to the number of field lines per area, like per square meter, right? How tightly packed they are. So if I wanted to calculate that for this now, right? Imagine that I've got this and I'm thinking about how strong his field is, maybe like say here. Some distance, we'll call this R away, right? So what would I do? I want to see how tightly packed the field lines are that far away. So what I might do is I might imagine drawing like a bubble around this charge in 3D, a little bubble with radius r. And I could count how many of these field lines punch through the bubble and then divide that by the surface area of the bubble. And that'll tell me how strong the field is, right? And so if I did that, you know what this would end up looking like, right? I would have some number of field lines divided by the surface area of that bubble. In this case, a sphere, right? Spreading out in 3 dimensions evenly. It's going to spread over a sphere. Now, if I went twice as far away, right? So now I draw my bubble twice as far out. So, right? And I count, and I try to do this calculation again. Now I'm a distance 2r out, right? Is this distance 2r? Well, if I calculate my field strength there, do you agree it would be the same number of field lines? Every field line that punches through this bubble will go on and punch through that bubble, right? There's the same number of field lines. It's just the area, the surface area got bigger. Well, So as I go further out, I'm having to spread that electrical influence out over a bigger and bigger surface. It's getting more and more thinly, more diffusely spread out. Kind of like light would get more and more dim as it gets spread over a bigger area. So you say, well, in 3 dimensions, if it spreads out evenly in all directions, what shape is it it's spreading out over? As I go, this, it's a sphere. The formula for the surface area of a sphere is 4 pi r squared. So my field strength, going to depend on those number of field lines. There's actually a symbol for that. It's a Greek letter phi subscript e. That's electric field lines. Um, that's my electric field strength. It's got a symbol capital E. So the point is that field strength, how strong the electrical influence is, should be proportional to 1 over 4 pi r squared, 1 over the surface area of a sphere. That's going to be true for pretty much anything that spreads out evenly in 3D. It's just like a property of three-dimensional space, just the geometry of 3D. That things spread out over a bigger surface area sphere, their intensity, how strong they are, is 1 over 4 pi r squared. So the electric force is this way, the gravitational force is this way, light is this way, radiation would be this way. If it spreads out evenly from a source in all directions, its intensity drops off 1 over 4 pi r squared. This is something that was like, I'm not sure if the guy who first thought of this was Robert Hooke, but he definitely shared this idea with Isaac Newton, and Isaac Newton used it to figure out his law of gravitation, and then proceeded to not give credit to Hooke. Anyway, moving on. So going back to where we were. Sorry, going back to where we were. We just figured out that this electric force should be proportional to 1 over, not 1 over r, but 1 over 4 pi r squared. So if I put these together, then I should figure out that that electric force should be proportional to Q1, Q2, and 4 pi r squared. Now, we said that this is directly proportional, so if I double this charge, it should double the force. And if I double this charge, it should double the force. So these have to be multiplied together. If they were added, right, if I had an equation where these were added, then if I doubled this, it wouldn't double the total, see? So I know they have to be multiplied together. And same thing here. So it's got to be, I can put these together and that's it. Now, I don't want to have it just is proportional to. I'd really like to have an equation so I can calculate. And so the question is this everything that goes in that equation or am I missing something? So one way of checking this is to say, well, I could think about units. If I think about the units, right, I'm just going to squeeze that in here. Force should be in newtons, right? Charge, the unit for charge is called the Coulomb. So this would be coulombs times coulombs. And then the unit for distance is meters. So that'd be over meters squared. Well, is a newton the same thing as a coulomb squared over a meter squared? Coulomb times coulomb over meter times meter. You're like, no. I know from F equals ma, I know that a newton is a kilogram times a meter per second squared. So if nothing else, then I need some sort of a conversion factor here to make the units come out right. Okay, to know like how many newtons go with how many newtons pushing on each other far away. There's going to be some kind of a constant of proportionality here. And so there ought to be some other constant there if I want to turn that into an equal sign. Now, it turns out, and I am telling you more than you really need to know right now, but why not tell you everything? If I want to make an equal sign, then the constant we're going to put in there, the symbol we're going to use is 1 over epsilon naught. So this will be equal to, and now I'm going to move the 4 pi, because that's a constant, move that over. So we really write it like this, 1 over 4 pi, and then to make the units come out right, we have to use this guy, times Q1, Q2 over r squared. All right. So what's this epsilon naught? Epsilon, it's a Greek letter. This is a lowercase Greek letter epsilon. It's kind of like a Greek letter E, right? But it's a lowercase one. In this case, what epsilon naught is, it's called the permittivity of free space, okay, or vacuum permittivity. So what this is, what it really is it tells you how many field lines a certain amount of charge will push out into space. It talks about how easily charge can make field lines, okay, on these special field diagrams. So like how it tells you, it's like a proportionality constant telling you like how strong the field is for this much charge when you're this far away. Now, to make the units come out right, we got coulombs over meters to be a Newton, but to be a Newton, I need kilogram meters over second squared. So to make the units come out right, what this unit has to be is I got to get rid of the, I got to get, well, let's see here. We just got to get newtons out on top, but this is on the bottom. So it's my units for epsilon naught are going to end up being, let's see, what it's going to be. It's going to be, yeah. It's going to be Coulomb squared per Newton meter squared is the unit. And when you do the math and calculate this, epsilon naught comes out to be equal to 8.85 times 10 to the negative 12. Okay, so it's 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. That's the value for epsilon naught, right? So if I calculate this out, I'm putting my distance in meters and my charges in coulombs, and then they'll cancel out, and I'll end up getting, because I'm dividing by this, it'll flip, and I'll get newtons out for force. Okay, so that's the way that this works. Now, because 4 and pi are constants and epsilon naught's a constant, it's more convenient to just lump them all together into one number. So if you actually took 1 divided by the quantity 4 pi times 8.85 10 to the negative 12, you could lump that together into just one value. And a lot of times in first year physics, we'll draw the equation that way, or write it that way. We'll say electric force is, and we'll use a symbol for this, we'll use a lowercase k, right? So it's k times q1, q2 over r squared, okay? Where if I took this 1 over 4 pi times that, the value for that k comes out to be almost exactly on the nose, 9 times 10 to the 9 newtons meters squared per coulomb squared. Yeah, see how the epsilon's in the bottom, this is on top, and so the units are like flipped upside down. Anyway, in 9 times 10 to the 9, that's just really easy to remember, and that's easy to work with. So a lot of times we'll just work with that with first year physics. It turns out, I said that this epsilon value, this permittivity of free space, talks about, it's a measure of how difficult it is for this charge to push field lines out. The bigger this epsilon gets, if you had a bigger epsilon value, you would get a weaker force, right? So it turns out that if my charge wasn't in the middle of empty space, if there was other stuff around it, that might affect how strong of a field you get. Again, this is beyond what you need for first year physics, but just since I'm here and talking to you, we'll put another constant in here to reflect that, to modify it. So if it wasn't going through empty space, it wouldn't have a naught there. It would be epsilon, not naught. And sometimes we can write that other epsilon with this other symbol. We'll say that this epsilon not naught, this value we'd have if it wasn't empty space, would be equal to this kappa times epsilon naught, where this kappa is called the dielectric constant for that material that we're trying to push electric field lines through. Don't sweat it for this year. I'm just mentioning to you that this epsilon naught is the real universal constant that talks about how much field a charge makes. But we lump it together with this other constant, and if we're just doing empty space, we ignore this dielectric constant, what other materials might affect it. So I just thought you should know the limitations on this formula. This is the way we're going to use the formula this year. The limitations are this formula is only for point charges that are this far apart. If I have, for our purposes in this year, if I've got charge spread out over an object, I'm just going to use the distance between the middles of the two objects. I'm going to treat it like all the charge is concentrated at the center. All right. Next year in AP Physics, we'll look at trickier cases where charges spread out over surfaces and in volumes. But for now, we're going to do that. So that's the first thing. This is for charges that are point particles, distance r apart. The second thing about it is we're assuming that they're separated by just empty space. Air, so vacuum, empty space, kappa is 1. So epsilon is epsilon naught. If I had air, it's like almost equal to 1. It's like 1.00007 or something like that. So for our purposes, we're not going to be like trying to dunk it in some other material. So this is going to be fine for us. Okay, when I write this equation like this, so the limitations are point charges and separated by vacuum or air. And then the last thing about I got to say two more things about this. This equation has a name. The person who first did the experiments to like kind of test this out and check that if I took two things of the same charge and moved them twice as far apart, the force dropped off 1 over r squared, and prove that when I had these two charges, if I took two identical metal spheres maybe, and I charge one of them and I check to see how it repels the other one, and then I take it and I touch it with another identical one, so now the charge is half as big, and you could show, oh, now the force is half as strong. Okay, now I can touch it with another identical sphere, now it's a quarter, I can see the force is a quarter strong. That proved this directly proportional, proved this one of this. His name was Charles Coulomb. So this equation is called Coulomb's law. And you might remember, hey, the unit for charge is the Coulomb, named after Charles Coulomb. So he got the law named after him and the unit of charge named after him. So this constant here, this lowercase k, that's the constant in Coulomb's law, is called the Coulomb's law constant. That 9 times 10 to the 9. Okay, I've got one last thing I got to warn you about using Coulomb's law, and then maybe I'll do a quick sample calculation. Last thing I got to warn you about Coulomb's law, and that is this. Coulomb's law is an equation we're using to calculate a force, right? So I might say, hey, here's my electric force, K, Q1, Q2, divided by the distance between the middles of the charges squared. Let's say I have this example like we had before. Here's a positive charge, separated by a distance r. I could go ahead and I could start putting in, calculating out. Now, when I put in K, 9 times 10 to the 9, Q1, Q2, and this distance, am I solving for this force or this force? And you say, well, Mr. C, they're the same size. You're solving for either one. But wait, electric force is a vector. It has a direction. We might choose to call some particular direction positive. So this one would be going in the positive direction, but this one's going in the negative. Can this equation tell me the direction of the electric force? In this case, this charge is positive, this charge is positive. The distance squared is always going to be positive. K is a positive. This is going to give me a positive answer, but I'm going in two different directions. Do you see the problem? What if I had a charge that was positive, one that's negative? You're like, well, if I had a positive and a negative, then they're going to attract each other. And my forces, again, the two parts of the force are going opposite directions, right? Again, it can't tell you the direction, this equation. So when we write this equation, we always have to remember that this equation is not telling us really the force. It's telling us the size of the force. It's telling us the magnitude of the force. So to show that, sometimes we'll use like absolute value signs on it. to remind us that this equation is just telling us the size of the force. Now, do I want to, so if this is just going to give me, I'd like to just make it always give me a positive then, and then I'll just remember this is telling me the magnitude. So k is always positive. A distance squared is always going to be a positive. But I might have negative charges, right? So I'm always going to take the absolute values of the charges too. I'm going to make sure everything's positive. So later on, if I have, say, something like this, right? I got a charge here, and I got a charge here. This guy's Q1, this guy's Q2. Maybe I have a third charge here. Here, we'll make this a negative. Call this guy Q3, right? If I want to find the total electrical force on this guy, Q1 would push him away like this. That's the electrical force on 2 by 1. Q3, this is a negative and that's a positive. These guys would attract. This guy would be attracted towards Q3. So there'd be a force here. That would be the electrical force between 2 and 3, right? On 2 by 3, right? The total electrical force, I'd have to add these arrows together. Now, when I add them, it's going to matter very much to me, like which directions these things are going, right? So I care about, this is not the best example. I should have done a different example first. I could put another charge, I'm going to just make it even more complex. Hey, look, there's a fourth charge here. Look, this is a Q4. Q2 is also going to get pushed. These are both positive, so it'll get repelled to the left. So I'd have a force this way. This is my electrical force on 2 by 4. So when I go to find the total force on this guy, if I think about the horizontal direction, I want to do forces right minus forces left. So I don't want a plus or minus, I don't want minus signs hiding in here. I want to just have the variable here mean how big is it, always be a positive number. And then I put the plus or minus on when I go to do the sum of the forces is MA. Don't we do like forces right minus left up minus down? So I might do FE21 minus FE24 equals the mass of charge 2 times the acceleration charge 2. You know what I mean? So the point is, I want to put the signs on myself outside the variable. I want these variables to always be positives, these F's. So that's it. That's the last thing to tell you about Coulomb's law, and that is we use absolute values of these charges. And that gives us the, so we're always going to get a positive value for Fe out of this equation. It can't tell us the direction. We have to use the fundamental rule of charge to figure out which way these forces are going to go, towards or away if they're attracting or repelling. And then do our right minus left, up minus down. We do add the forces. By the way, if I had this case with these 4 charges and I wanted to find the total electrical force on Q2 here, how would you do it? I've got 3 different arrows, right? How do you add them when they're at different directions? These are vectors, and we have to add vectors. In your packet, you'll find there's a page that describes to you the process of how you add vectors, how you add arrows. And that is something you should look at and make sure that you follow along with. As we're doing some of the problems here on worksheet 3, we'll be doing some problems where we have to add multiple electric force arrows together eventually. I'll talk about it in class, I'm pretty sure here, before I have you try some of those trickier problems. But for now, just the first problem, we're just going to worry about having 2 charged objects and how they're solving with this equation for the size of the force between them. Okay, that was way more information than I thought I would I'd be putting into this one video. I should probably stop this video now. But I'm just going to remind you one more thing, just so that the data is here on this video, and that is we talked about how charge is measured in coulombs. A coulomb is a very, very large amount of charge. You are normally not going to see a coulomb's worth of charge separated out in one place. That is not something you see normally. Let me show you how you know that. Let's take this equation, right? Let's say if I could take a Coulomb of charge, right? Separated out. So I have a Coulomb of positive charge here maybe, and a Coulomb of negative charge here. And maybe I've got them separated by 1 meter of distance. How big would that force be between these guys? They would want to attract each other, right? How hard would they pull, right? That electrical force. Well, if I use the equation, my electrical force, right, the magnitude of it would be K. The K is 9 times 10 to the 9. The charge is, I'm saying if I had 1 Coulomb times 1 Coulomb, in that distance, if it's 1 meter, I'm going to square, this would be what? 9 times 10 to the 9 newtons. That's what? A 9 with 9 zeros after it? So that would be 9 billion? Is that right? Wait, this is thousands, this is millions. Yeah, 9 billion newtons. So it'd be 9 billion newtons of force trying to pull these things together. You're like, yeah, you're not going to see that all the time. So normally when we do things like in lab, when we're taking those like friction rods and rubbing them with the fur and the silk, we're typically separating a tiny little bit of charge, way less than a Coulomb. Typically with those friction rods, I think the charge is about uh, 10 to the negative 6 coulombs. Now, 10 to the minus 6, you know how like uh, a tenth is a deci in the metric system, a hundredth is a centi, a thousandth is a milli. You might remember, I don't know if you remember, but 10 to the minus 6, that's 1/1 millionth, right? So if I have 1/1 millionth of something, the metric prefix is micro. And the symbol we use for that is, so if I had like say 3 times 10 to the minus 6 coulombs, that would be 3 microcoulombs, which I would write with this symbol. Okay, that's what this 3 times 10 to the minus 6 coulombs means. So a microcoulomb is a millionth of a coulomb. Now this symbol for micro, hey, that's a lowercase Greek letter mu. You remember us using that symbol for the coefficient of friction. Again, here we're using it for something else. It's part of a unit label, so it's not a variable here. So you wouldn't get them confused, right? But that's it. So if you see microcoulombs popping up in things, because that's a more convenient size charge for charged objects, that's why. Um, and since I'm doing this, the other number that I always point out is the smallest piece of charge that you're likely to come across would be the charge on one proton. The charge on a proton is called an elementary charge, okay, which has a symbol E, lower e, that's an elementary charge. So when you say a charge of protons plus one, that means it's 1e, one elementary charge. And one elementary charge is equal to 1.602 times 10 to the negative 19 coulombs. So that's the charge on one proton. Negative this would be the charge on an electron. Um, so when you talk about protons, electrons, it's a teeny, and no one's surprised that protons a teeny tiny amount of charge. But even when we're, a coulomb is just a truly large unit. And so we're almost always going to have these like tiny fractions. So when you go to do these calculations for Coulomb's law, you're going to be dealing with these small bits of charge usually. So when I do the calculation, it's going to look like this. Maybe I have, let's do one real quick. Maybe I have a charge here that's 3 microcoulombs and a charge here that's negative 3 microcoulomb. Let's make it, I'm sorry, let's make it negative 8 microcoulombs. And we'll say they're separated by, I don't know, 3 centimeters, right? And I want to find the electrical force between them. Then when I solve this, and I'm using my equation, KQQ over R squared, Coulomb's law, then my K is going to be 9 times 10 to the 9. My charge on the first one is going to be 3. Now the micro means 3 times 10 to the minus 6. And the other charge is negative 8 times 10 to the minus 6 That's negative 8 microcoulombs. And that 3 centimeters, I am immediately going to convert that to meters. So I know that it's 100 centimeters a meter. A centimeter is a 1/100th meter. So it's going to be, divided by 100, be 0.03 meters, right? But remember, it's got to be squared. So that's what my calculator is going to look like. And yes, I'm doing absolute values here, and I would be doing absolute values here. So that negative there is going to go away. So it'll be just 8. So when I do the math here, right, I've got all these powers of 10. So if I have everything being multiplied together like this, if everything's being multiplied together, you can multiply them in whatever order you want, right? So what I usually do is I'll rewrite, when I punch in my calculator, I'll punch it in like this: 9 times 3 times absolute value, so 8, right, divided by 0.03 squared. But the powers of 10, the 10 to the powers, those exponents, I'll just do those separate. 10 to the 9 times 10 to the minus 6 times 10 to the minus 6. I remember I can just do that in my head. You just, add the exponents. 9 and negative 6 and negative 6, that's going to be times 10 to the minus 3. Okay, so that makes it easier on me because then I'm just punching this in my calculator instead of this long strand, having to be careful with parentheses and stuff. So that's my suggestion to you, is that when you go to do these calculations, you can try setting aside those powers of 10 to make it a little bit nicer. So if I do this, oh no, oh no, this calculator is dead. That's okay. Gotta use the physics calculator. If I use the physics calculator, you say, well, I'll go ahead and I'll do 9 times 3 times 8 divided by 0.03 squared, and then I'll multiply that by 10 to the minus 3. They'll just move decimal point 3 places over, so that 240,000, but then times 10 to the minus 3, and that just makes it be 240 newtons. Now, just pointing this out, 3 microcoulombs, 8 microcoulombs, 3 centimeters apart, right, like this, that would be 240 newtons already of force. So, if it was 1 microcoulomb each, would be 10 newtons. That's starting to get to the ballpark of the kind of size of forces we're actually seeing. So yeah, we're usually not separating that much charge with static electricity. Okay, that's it. Hey, that 240 newtons, this guy, that 240 newtons would be pulling it to the right. This guy, that 240 newtons, would be pulling it to the left, right? So if I care about the directions, I got to kind of talk about them separately because they're going to be opposite directions. Okay, that's it. That was probably longer than the video needed to be. Again, you now know what you need to know to try some problems with Coulomb's law.